Cool. Hi, my name is Brad, as he said. I came down here from Santa Barbara County, Carpinteria, if you've ever heard of that. I work at Procore, construction management software. We do a lot of JavaScript. We write our JavaScript in a functional style. And what exactly does that mean, functional programming? Really, you're doing functional programming when you're combining a host of functional techniques. You don't have to, you can pick and choose some of these, but it's really when you use them all together that you've achieved functional programming. The green checks here, these are things that are built into JavaScript natively. The yellow squiggles, those are the things you can add with some third-party libraries, and the red stuff, there's no hope. But fortunately, JavaScript has enough built in that you can program in functional style, basically with only a few third-party tools. This was originally a 45-minute talk that I cut down to 25, so I can't talk about all this stuff tonight. Tonight we're going to focus on that first one, immutable data structures, and also lazy sequences, and those two in combination, and you can see some really powerful stuff that happens there. So, immutable data structures. I still have to go fast, right? Even though I've cut it in half, I still have to go fast. If I go way too fast, someone just raise their hand. Like if you have a question, if there's some term that I throw out there that you don't know the answer to, it's okay. Otherwise, I'm going to go through this pretty quickly. Immutability in JavaScript. The JavaScript array class is not immutable by default, obviously. You can add things to it and change it. So how do we achieve immutability? You could just use some discipline and not change things. If you create an array, don't change it. I don't say that as a joke. By the way, our host told a joke, so I have to tell a joke. This is the world's shortest joke. It's a joke in 2 words. Ready? Pretentious? Moi? Yeah, get that excitement meter up. Woo! Okay. But really, you could just be disciplined and not mutate it. That's actually not crazy. It's not a joke. Or you could use one of these third-party libraries. Mori is David Nolan. That's the one that backs ClojureScript. If you're a Clojure or Lisp developer, it'll look real familiar to you. It uses underscore style syntax. Immutable JS is my choice. That's what I'm going to be using in this presentation. That's from Facebook. It's a really kick-ass library. And here's what it looks like. So here I've got this array, 1, 2, 3, 4, 5. I'm calling this function around it, list. That converts it to an immutable list. Immutable, of course, means a list that cannot be changed. In other words, now that that list is 1, 2, 3, 4, 5, I can't go and add anything to it or modify its contents. Kind of. And I'll explain why a little later. And here we have a higher order function. That's just a fancy way of saying it's a function that takes another function as an argument. Hopefully you're all familiar with this, or I apologize, you're probably going to be totally lost for the rest of this, but, you know, bear with me here. So what we're doing here, we've got 1, 2, 3, 4, 5. We pass in a function that multiplies it by 2, and we get back to 4, 6, 8, 10. That's your basic map function. And I want to throw out one more little example here. This is going to look kind of weird, but this is going to come into play later in the demo code that I show you. So here I'm taking 1, 2, 3, and for each of those, I'm mapping it to an array containing 4 elements, left, right, up, and down. What you get back is a list of arrays. So like basically nested arrays, arrays of arrays. If that's not what you wanted, if you want these all in one list, right, you use this function flatMap. So now I get the same 12 elements, but instead of arrays nested in arrays, it's just one big array. This is going to come in important later, come into play later into my demo. That's why I'm showing this. But that's another higher order function, a function that takes a function. Okay, cool. So the other technique I'm going to talk about tonight is laziness. Laziness is very, very, very cool. That's when you do list operations and they don't actually fire off or execute until later. So here, this range function, that's built into Immutable JS. It gives me a range between 2 and 50. Dot filter is going to return another list which contains anything for which this inner function here returns true. Right? So I made a function is prime. It's boring math stuff. I'm not going to show you that. But this is real easy. So I get back the prime numbers between 2 and 50. You know, very cool, very simple. That's a very, very simple problem. Where it gets difficult is like, what if instead of prime numbers between 2 and 50, I want the first 50 prime numbers? Or let's say I want the first 1,000 or the first 5,000. That becomes, or first 10,000, gosh. That becomes a little tricky because like, how do you know where to start and stop? Let's look at this again. What's the 10,000th prime number? Is it a billion? Is it a trillion? Is it a quadrillion? I have absolutely no idea. So with this range, I don't know where the upper bound is, right? I don't need to know how far I go. So with that in mind, it's real hard to do this functionally. You might try to take the procedural approach like this, but that's not functional. That's what we're trying to get away from, right? This is where laziness comes to the rescue. So here we've got a range again, this time from 1 to number.maxValue, which is some ungodly huge number, right? And we're calling filter against that and returning, filtering out the numbers that are prime. And then we're taking the first 10,000. Now take a close look at this function, because you might think that before we take the first 10,000, it's going to evaluate all the prime numbers basically between 1 and whatever that godly, huge number is. Not even exaggerating, the sun would die at heat death before that program finished, right? It's impossible to run this. It would take trillions of years. Obviously, it's not doing that because we're getting our result back. This is laziness in practice. It doesn't do anything until you do .take. So we've got kind of this filter operation, which is sort of queued up, ready to operate on this practically infinitely long sequence. And it's only when we .take that it actually evaluates it and stops at the first 10,000. So that is the magic of a lazy sequence. Very, very, very cool. And that's how we solve that problem without defaulting and going back to the boring old procedural approach, with our while loop, which is not what we want. So what's really cool is we're going to combine these lazy sequences and immutable data structures. So I'm going to put this together to solve a problem. This is a problem. I took a course on Coursera. It is called The Principles of Functional Programming in Scala, taught by Martin Odersky, who's the inventor of Scala. And this is where I ran into this problem. So here's my awesome, super modern HTML5 isomorphic reflux. Just kidding, it's a Flash game. I didn't write this. But this is Bloxers. I wrote a solver for this game of Bloxers. So let me show you Bloxers first, and then I'll show you the solver. Okay. Stage 1. Okay, so the idea is this little block, what I want to do is get it in that hole over there. Woo! Just like that. Cool, right? No problem. So this little thing here, there's some bridges. My simulation doesn't have bridges, so you don't have to worry about that. But you just want to get this block kind of in this little, oh boy. Right. Shit. All right, let's try that again. Someone help me out. Oh, shit. That was Flash. JavaScript, that never would have happened. No. God, I suck at this. Ah, shit. There we go. Boom. All right, let's see. Ready? No, hold on. Okay. All right, very cool. That is the most complicated part of this. Now, I want you to take a look at this level for a second. Memorize that shape there. Oh yeah, want to see it again? Sorry. All right, there we go. See that? Cool. There it is in ASCII, okay? The S is the start, the G is the goal, okay? What my program does is it finds the most efficient route to solve that puzzle. There it is. All right, this is always the fun part. Let's see. I gotta get these next to each other, side by side. I've done this before. I've given this speech a few times. All right, you're not gonna be able to see it all, but here it goes. Right, up, right, up. Oh, shit. I hope this is the right level. Right, up, right, up, left, down, right, up, right, down, right, up. I got it. You couldn't see it, but I got it, okay? Cool. So this is a solver for this problem. It finds that is actually, it didn't look like the most efficient route, but that is the most efficient solution to that problem. I solved that using functional JavaScript. So how do we do that? What is our algorithm here? Whoops. Okay. So if you envision this, the way we solve this is we envision the possible moves as a tree. So starting from the very beginning, I have 4 possible moves. Left, right, up, or down. From each of those, I have 4 new possible moves. So for the first set of moves, there are 4 possible. For the second set, there's 16, minus the red nodes, which is where either you fall off or you're in a position you've already been in, and we don't evaluate because we don't want to get in an infinite loop, right? So what we want here is what's called a breadth-first tree search, if you remember that from your algorithms class. But this is a functional version. It might look a little different than the one you're used to. The normal one uses queues and stuff like that. The functional version is much slicker. And this is the order we want to evaluate in, because to get the most efficient route, we want to get the first tier first, the middle tier, I guess you'd call it, because those are the possible first moves, before we go and evaluate the second 16 possible moves there, which are the possible second moves. So that's why it's breadth first, because that's the order we're evaluating the possible moves in. And our functional algorithm works by first starting with that first block and flat mapping that to the 4 directions. Do you remember the flat map slide I showed you, where I have 1, 2, 3, and I flat map it to left, right, up, down, right? And we get and you get right times 4, right? So this would be 1, 4, 16. So then from the second level, we take those 4 and we flat map them to the 4 directions, and then we go from 4 to 16, 4 times 4. So once we start flat mapping these levels together, what we're going to do is we're going to concat, which just means basically take the first level and tack the nodes from the second level onto the end. Now think about for the second, we've got an immutable data structure here. We've got a list that is immutable. We can't append something to an immutable array, can we? That would sort of break the rules and kind of ruin the whole point. So clearly there's a catch here related to the data structure we're using. And that has to do, we can do that because it's a functional list. So just going back, like what are the possible options here if I take one list, concat something to the end of it, and that's supposed to be immutable? Well, the first thing I could do is make a copy, right? I could have the original be immutable. I can concat. I can make a total brand new, fresh in-copy memory with the new parts concatted on the end, right? And then you would have achieved an immutable list. That doesn't sound very efficient, right? Because we're like copying a whole list. That sounds pretty slow, doesn't it? Turns out there's a better way, and I'll explain to you how this data structure works. So here's our immutable JS list, just like you saw before. 1, 2, 3. Dot first is 1. Dot rest is 2, 3. These are important methods, so remember these. Dot unshift pushes something onto the front. So I've got 1, 2, 3. I unshift a 0, and I push a 0 onto the front. Just to prove that it's in fact immutable. So here we've got list, which is 1, 2, 3. New list, we push the 0 onto the front, and when we console.log list, it is indeed unchanged. It's still 1, 2, 3. You see that? That's why it's immutable, because the original reference still points to 1, 2, 3, not 0, 1, 2, 3. So once again, how are we doing this efficiently? Any guesses? It's a linked list. Remember that thing from data structures that you've heard about and have never ever once used or realized why it's important? Right? This is how we do it. Because we've got 2 references here. The original reference points to the node 1, which is still 1, 2, 3. Whereas the new reference points to the 0. Now we've got the awesome combination, which is an immutable data structure that we can change without inefficient cloning or anything like that. It's a beautifully elegant solution using a simple data structure. Very, very, very cool stuff. So what we call this now is a persistent data structure. That's a terrible word, persistent. You think of like saving stuff, like databases. All of functional programming actually has terrible vocabulary. Monads and monoids and applicative functors. If you read that stuff and you get lost, you're not the only one. It's all from this obscure branch of mathematics called category theory. It sucks. I don't know who thought of these terms. Yeah, so that is a persistent, right? A persistent is immutable, but immutable is not always persistent. This linked list is a persistent immutable list. Right? Okay, cool. We also actually use this twice. If you think about my video game solver, in order to spit out the answer at the end, we have to keep track of the history as we go. We also need that so that we don't go in an infinite loop. We have to find positions we've already been at so we don't loop forever. So I've got to kind of keep this history, which is sort of a linked tree. Here's an example, right? VH 1980. This is a rock reference to a rock band, Van Halen. They used to have this lead singer, David Lee Roth. They booted him and added Sadie Hagar in 1984. So I start with David, who's the original lineup. From the inside out there, .rest is going to return the 3 at the end, minus David, right? And then I unshift Sammy onto the front. What have we done really then here? These are our references now. So we've kind of turned this list into basically a linked tree. Once again, memory efficient. That's the beauty of persistent functional data structures. Cool. And that's the way I keep the tree. Basically, as my program executes, that's the way I keep that history, so that at the end, when we solve the answer, I can spit out the answer. That's the history. That's how we keep the history. Very, very, very cool. Let me just show you a little bit of the code from the block source solver. So we saw this starting out. Is that big enough? Should I make it a little bigger? Yes? No? All right, cool. Here is the program. So we're going to see a few functional techniques. How much time do I have, by the way? When am I supposed to stop? You got time? Cool. First of all, where are we starting off? IsOnBoard function. All right, very cool. I'm calling this IsOnBoard. This is a higher order function. If I look at IsOnBoard, it is a function that returns a function. That's one of the parts I skipped out in shortening this, is those higher order functions, but there it is in practice in case you're wondering. This level array here this is called partial application, because this function that I return still has a reference to level array. Why do we do that? It's instead of object-oriented composition, this is functional composition. I'm getting a function that tells me, that takes a level, well, sorry. The function I get back takes a block with its position and tells me if it's still on the board. I've got another one here, isGoal. That takes a position, and don't worry about what that actually is. It's some arrays nested with some objects, not important. IsGoal function, right? I pass in the goal position, I get back a function, right? Pass in a position to a function and get back a function that tells me if, in fact, I've won the level. Cool. I've got some starting blocks, starting move lists. Okay, so here's where it kind of gets fun, is flatten tree lazy. As you can guess, that's my algorithm. The flat maps and the concats, right, that do my breadth first tree search. I'm passing in that IsOnBoard function. That's real nice, because now the flatten tree lazy implementation doesn't need to know anything about the stuff outside of it. You know, think of like object orientation. You'd pass in some kind of like some other class, right? But in this case, I'm passing in a function. Very clean. I pass in the data I need for starting, and I get back a lazy sequence. So flatten tree lazy, I'll show you the implementation, which is my flat map concat, which does the tree. This one actually got a little messier than I liked, because I had to do 2 flat maps, and that's because blah, blah, blah. Immutable JS doesn't support a real lazy concat, so I had to work around it a little. But it's all right here. There's my move list. I flat map that to the set of next legal moves. Then I go and, where's concat? Oh, concat's way up here. I concat, and here's my recursive call to flatten tree lazy. So you can see it's a recursive function that builds this tree shape structure by appending stuff onto these immutable arrays, in a very memory efficient and fast way. So it's all right there, very cool. This IsOnBoard function, I should have named this like isSuccess, because, that's functional composition, because now flatten tree lazy doesn't have to know anything about the boards or anything related to this program. I could take this out, post it, on GitHub as some standalone thing, and you could use it in another program. Just pass in the function that tells you when to stop. So that makes it real reusable. That's functional composition for you. What's very, very cool is that here when I call it, this is a sequence, but it's a lazy sequence, because everything in Immutable JS, these data structures are lazy by default, which means this has not executed yet. Consider this program. It's not just going to find the first solution. It's going to find all the solutions. And for a big level, that could be huge. In fact, I could run out of memory before I get there. But I don't have to worry about that. Just like with my primes, I don't have to worry about calculating till the sun burns out. I don't have to worry about the fact that this algorithm finds every solution, not just the first one, because it hasn't even fired off yet. So now that I've got this lazy sequence, how do I find the answer? Simple, using .filter. Just like how you find an element in the list. And you pass in a function, my isGoal function, what's that going to return? Another lazy sequence that theoretically, though it hasn't been calculated, contains all the answers. What do you do to get the first one? Call .first. Right? So this whole thing's coiled up like a snake, all these list operations stacked onto each other. It doesn't actually fire or do a single computation until I call .first. Then it uncoils, flat mapping, concating, flat mapping, concating, flat mapping, concating, evaluating the tree breadth first until it finds the answer and returning only the first answer. Very cool. That's the combination of immutable data structures and lazy sequences. Did I lose anyone? Got it? How much time do I have? All right, cool. Just a few more little, functional tidbits and cool things that I didn't mention before, but I'll mention now.
Sorry, so it's the first one that took that many steps.
It is the shortest solution. Yes, it's the first solution. It's guaranteed to be the shortest one. Here's I've got a few data types in here. This is just an object with a row and column that represents a position. Here's just one that represents a block, which takes 2 positions. These little functions like these are like little factory functions. This is a very common paradigm. If you look at my function, so left takes a position and moves it to the left. I'm passing a row and a column to that position function, which gets me back a new object. Very important. I don't have like I don't have an object with like a row and column and I'm changing one, like incrementing it when I move to the left. That would violate the immutability rule, right? We never mutate a variable in functional programming. We only get back new ones based on the old. That's why you do these like little factory functions like this that take a position and return something brand new. This whole program, you can tell this is pure functional programming because it has no side effects. I never once take a variable, set it, and change that variable. Not once in this whole program. This whole thing could be done without variables at all. You see these right here? These are just for readability. I could actually just collapse those down into a bunch of nested functions. It wouldn't be very, very readable, but you could do it. And it would, in other words, this whole program could be done where the only variables are the function arguments. Because I never have to set something and change it. I definitely don't set any globals or anything like that. It's just one basically giant long string of functions. The only thing that violates that is the very first line, where I'm setting the level, and the very last line, where I print it to the console, which is by definition a side effect, because that's I/O. So that's how you can tell that this is a pure functional programming. So let's have just a little fun, and let me show you just 1 or 2 more levels. When you want to bet this crashes, stupid Flash. Okay, this is not the one I want here. I'm just going to refresh this real fast. Oh, no, menu. Ah, shit, too late.
Do you have to worry about the stack?
Yes. Good question. What he asked was, do you have to worry about the stack? If you're recursing, the stack grows and stack grows and stack grows, and if you grow too big, it will stack overflow. That is a concern. ECMAScript 6, or what do they call it now, 2015, native has tail call optimization. So if you put the call in tail position, it will optimize that, crush it into a single stack frame, and then you don't have to worry about it. Of course, it doesn't work if you're transpiling using Babel, right? It has to be native ES6. So you would not want to process like 1 million rows using recursion in the browser, or you run that risk. But most of the time, you don't actually have to do that. Okay. So let me show you another level. I forget what the level is, actually. 189493. 189493. Come on, come on, come on, come on.
Have you worked with lazy jobs?
Hold on. 189493. I have used lazy, and it does the lazy part, but not the immutable part. Facebook Immutable.js is much cooler, in my opinion. It's kind of the next generation.
Have you looked at ES6 spreads?
ES6 what?
Spreads?
Spread operators? Yeah, I don't know how they're similar though. Or maybe I don't understand.
Stuff immutable and tail head call stuff.
Oh, cool. I haven't gotten too far into that. We use it at work, but I'm not actually on the front end team. All right, so here's this level. There's a little X there, which does actually make a little piece pop up. The question is, can you get to the goal without actually hitting that little piece? Well, let's find out. Here's the level. You can see I've got the start in the actual starting position and the goal in the actual goal position. So level 2A, level 2A. Error, no solution found, right? That is not a Stack Overflow, by the way. It actually evaluated all the possible potential games and found that it could not find an answer. You notice that was pretty fast, too. Node is fast. All right, so clearly, to do that, we actually have to hit the X and change the level a little bit. In the second version of this, all I did was just move the goal to where the X is. So we're going to hit the X first. So let's see here. 2B. All right, here goes nothing. By which I mean here I try to get these tabs next to each other without embarrassing myself. Oh, that was easy. Okay, here it goes. Down, left, up, right, 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 right. Wait, that was the old one. No, that's right. Right, down, right. Ah, okay. The only change that made was to add this one little corner piece right down here. That's the only difference, right? So now, in this one, I added the little corner piece. I moved the start to where the block is now. The goal is here. So level 2C. All right. You're probably not going to be able to see it all again. But maybe I can try. All right, here it goes. Whoops. Ah. Okay, I hope this is right. Here it goes. Left, up, left, 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 down, right, down, right, down, right, 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 up, up, right, down, left, up, right, right. Come on, Flash. Hold on, where was I? Down, right, down. Oh shit, I lost track. Let me try again. I did that on purpose. Let me try again. All right, don't distract me. I gotta start all over. Hold on. Do I have time to go through it?
Speed run.
Down. Oh God. No, I gotta start with. Oh yeah. Okay. Down, left, up, right, down, right. Okay. Come on, baby. You got this. Oops. Left, up, left, down, right, down, right, down, right, up, right, down, left, up, right, down, left, up. So, we got it, almost done. Come on. So what did we learn? I didn't talk about this much, but put all the state in one place and use as little stateful code as you can to get the job done, which means don't mutate variables. Immutable data structures give us peace of mind because there's a whole classes of bugs that they avoid. Have you ever passed a list down to something, modified it, gone back to the calling function and been surprised that it changed? We avoid those bugs. Recursion and linked lists are awesome. Lazy sequences are super powerful. Higher order functions for functional composition are great. Highly recommend this book, Functional JavaScript by Michael Fogus. One of my favorite books of all time. This code is on GitHub. Brad Urani, that's my name. There's also a Ruby version if you're into Ruby. Functional programming in Scala on Coursera. If you want to solve this problem yourself in Scala, take that course. It's amazing. I'm Brad Urani. I'm addicted to Twitter. Follow me and I'll follow you back. Connect with me on LinkedIn. I've got a blog, but I never update it. But if you want to read stuff I wrote a year ago, that's fine. I work in Carpinteria, which is a beautiful little beach town just about 5 miles south in Santa Barbara. It's literally paradise at Procore, which makes cloud-based construction manager. That's the view from our office. It's the only place you can whale watch while you work. It's a runaway unicorn. We're all going to get rich. And we're hiring front-end, back-end, JavaScript, React, Reflux, ES6, all the coolest stuff. Come see me if you're interested. Questions? Yeah.
Full talk online somewhere?
We'll put it online. All the talks are recorded. So
This one, you're talking about the 45-minute version? The Ruby version is recorded. If you go to my blog at Fractal Banana, you can see the Ruby version, even though I kind of screw it up because the screen's not showing in the beginning and I curse a lot. But I will be giving the full 45-minute version at Santa Barbara JavaScript on September the 8th. If you want to make the trip to Santa Barbara, it's worth it. It's beautiful. Come and see me talk there. Yeah.
When you were talking about Van Halen linked lists, what if it wasn't the first element that changed, but one in the middle? How would that?
You can't really do, well, you'd have to sort of like back out by doing, well, I don't know, it wouldn't work as well.
Okay.
I'll give you that. I'll tell you that much. Yeah.
Can't be done is a good answer.
Okay.
So is there a way when you're learning this and building this up to like visualize what's going on somehow besides just like output?
Oh, well, I tried. My little tree things weren't, they didn't visualize. Oh, do you mean like visualize dynamically as you're going? No, not that I know of. It requires some really sick JavaScript, like altering the array class and stuff like that. I don't know. That'd be cool. Actually, there's a talk from Strangeloop where a guy does that. He visualizes data structures by hacking JavaScript, the base classes. Yeah, in the back.
Do you have any opinion on RxJS or Lambda.js?
So I've heard I don't know one from the other. I've never used either, but those are reactive frameworks, right? Reactive is functional programming applied to user input. Like, so you're basically treating like a bunch of clicks as like a list and running like map and reduce and your other higher order functions against it. That's really, really cool. You probably want to start with the functional stuff first and then learn reactive next. Yeah.
So I've never heard anyone say this, but like JavaScript garbage collection, have you had any, like, does everything stay to the end since you're using a linked list, it's less memory, but like, is it, if you're doing tail recursion or something like that, is it smart enough to like throw stuff out?
Good question. I don't think so. I think as long as there's a reference, it's not going to be collected. And since I didn't actually peel off nodes of the linked list, I think they're going to stick around until the final solution's found. Yeah.
So as you're building this, does it making testing, does it make it easier because you know what parameters to put in and your expected result?
Yeah, it does. Because every function in that program takes arguments and returns a result. It does not modify any global variables. You know, imagine a function that takes some arguments, changes a global, and returns a result. Well, it's really easy to write a test against passing something in and getting the result back, but how do you test that you changed the global? That's messier, it's much harder. These pure functions, as they're called, with no side effects, where it's just every function gets something and hands something back, are so easily testable, they're like embarrassingly testable. So yeah, pure functional design is much more easily unit tested. Yeah?
When you're talking about the lazy functions, is that the immutable library is what decides that it's going to be loaded in that order?
Yes, it's immutable. There's some really, really smart stuff happening behind the scenes. Taking things that you enter in series and then parallelizing them element by element. The people who did that are geniuses. It's really, really cool. I have a hard time figuring out how it works, but that's exactly what it does, yes. Cool. Anyone else? Cool. Well, thank you. Whoops.